students, and welcome to a phase-changing week here. This week, we're going to be talking about changes in phases of matter. But before we can talk about the changes that take place, we have to talk about phases of matter first. And so this week's topic is phases of matter. If you haven't done so already, please make sure you open up your books to your lesson notes page and let's begin. So, phases of matter. If I were to ask you to list for me what are the phases of matter, what might you say? All right, many of you may have given 3 phases of matter. Maybe some of you may have even given a 4th phase of matter, but did you know that there's talk of even more? But let's begin with the first basic 3, and wrong button there. Let's begin with how phases of matter are determined. This will help explain some of the phases that we're about to discuss. So when we talk about phases of matter, we're talking about, they're also called the states of matter or phases of matter. It's a characteristic that matter possesses given the arrangement and the speed of particles that make the matter up. And that arrangement and the speed of particles can change. And when the arrangement and the speed of particle changes to various critical points, then we as scientists and as normal human beings, we can view and observe and we can characterize and we can determine that a particular sample of matter might exist in one phase or state of matter as opposed to another. And so we're going to be exploring the names of these different phases or states of matter as determined by particle arrangement and speed. And you can kind of get a sense for where we are going here by looking at this diagram and the different arrangements of particles in solids, liquids, and gases. I'll give you other illustrations of this as we go on as well. But let's begin with the first phase of matter, which we know as solids. We've known about solids pretty much ever since we were born. When we started putting our fingers in our mouths and other objects in our mouths, we pretty much had a good understanding of solids. And here are just a couple of examples. A brick, obviously an example of a solid, and crystals here. What beautiful crystals, these quartz crystals. Certainly another example of solids. But in terms of what's going on within these types of materials that we call solids, this phase, well, how do we really describe it more scientifically? Well, solids have a definite shape and a definite volume. And I've underlined some words here for a reason. It's probably a good idea for you to underline them in your notes as well, because you're going to have to be able to describe and define these different phases of matter, starting with solids. Solids have a definite shape. What does that mean? Well, a definite shape doesn't mean it has to be a geometric solid, such as a cube or pyramid or what have you. It doesn't have to be that, although it is helpful if you want to measure it. But a definite shape means that if you take an object in your hand, like this sphere, whether you hold it here or here or here or here, it's a sphere. Now, again, this is a regular geometrically shaped object, but it could be a non-geometrically shaped object like, here we go. I got something in my pocket here, like these keys. These keys aren't necessarily geometric shapes here, but these are solids. And these solids have a particular shape, whether we hold it here, 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 or whether we lay it on a surface. They have a shape that does not change unless we modify it by smashing them with a hammer or bending them in a vise. But a definite shape means that its shape is not changed unless we change it. So, definite shape and a definite volume. And what we mean by a definite volume is that we could actually measure, like, let's take this sphere once again, this ping pong ball, and we take something like a graduated cylinder. Using the displacement method, we could put water in this graduate, put the ping pong ball in the graduate, push it into the water, and measure the volume of that solid object. The volume of a solid is definite. In other words, once you determine the volume of a solid, it remains the volume of that solid unless you do something to it to change. But under normal, regular conditions, like in the room, a solid's volume is its volume. And we'll see how that varies from one phase of matter to another phase of matter. For solids, this might be common sense to you. Solids, definite volume, definite shape. We kind of have a pretty good understanding of that for most of our lives, I would imagine. But things do change as we change the characteristics of particles. Let's move to particles here and stay with solids for a moment. If we look at this diagram, we will see that in this box shape here, which is illustrating an example of a solid, the red circles are representing particles. And with solids, the particles are packed tightly together and move very slowly. Now, notice I say slowly, not stopped. If you think back to our topic on heat energy, and we learned about the Kelvin scale, do any of you remember what the Kelvin scale is based on? Hopefully you said absolute zero. And what happens at absolute zero? Perhaps you said there is no kinetic energy. There is no motion. Absolute zero is the temperature at which all molecular motion stops or ceases. So anything above absolute zero, there is going to be some motion of particles. Now, with different solids, there might be more motion than others, but in all cases, solids have particles that are tightly packed and move very slowly. I'm going to go over to a close-up view here and give you an illustration using our friendly ping pong balls. So here I have a plastic container. It's hollow. And inside of it, I have placed ping pong balls to represent particles of matter. Now you can see I have pretty much jam-packed the ping pong balls into this cube. And if I shake it and you listen, you can hear a little bit of jiggling, but not much, because the ping pong balls are so tightly packed together. If we had our magnifying glasses on and we could peer into the sample of a solid and look at the actual particles, it might actually look something like this. Particles would be very closely packed together and there would be very little movement. We'll see how that will change with another phase. But I want to pick up this idea of very tightly packed particles in matter. So let's go ahead, head back over to our PowerPoint here for a moment, and I want to add some information. Because particles are packed so tightly together, there is a lot of mass in a particular volume of space. And as a result, solids tend to have a higher density when they are in the solid phase, as opposed to when they are in other phases of matter. Other phases of matter. Now, I say tend to for a reason. This is not a universal law. In fact, there is one really notable exception to this. And that one notable exception is water. You see, water, if this were an ice cube, the particles, when water is in the solid phase, the particles actually spread out. They take up more room, which means even though they're still tightly packed and they are still moving slowly, they actually take up more volume. And so the density of water when it's a solid is actually less than when it's a liquid, which is why ice floats. But that's the exception, not the rule. And we've talked about this before, how wonderful it is that water is the exception and not the rule, because otherwise there'd be no life on this planet, because the oceans would freeze from the bottom upwards and there'd be no liquid water on this planet eventually if water was like all other materials when they turned into a solid. But by and large, most other materials in the universe, when they are in the solid phase of matter, their particles have a higher density. And so most materials, when they are solid, if you put them into a sample of their own liquid, the solid form will sink to the bottom, unlike water. And since we're talking about liquids here, let's go on to that next phase of matter, which we call liquids. Here are a couple of popular examples of liquids that you probably utilize each and every day. A good old glass of milk and a glass of water, both of which are considered liquids. You could think of many other liquids, I am sure, as well. I mean, juices are liquids. The ocean is liquid. Many other liquids. Mercury at room temperature is a liquid. But let's talk about liquids here from a more scientific perspective. Liquids, unlike solids, liquids have no definite shape, but they do have a definite volume. Well, what do we mean by no definite shape? Well, let's take this graduated cylinder again for a moment and imagine that we filled it with water. What shape would that liquid water have? It would have the same shape as the graduated cylinder, the same shape as the container that it was in. In other words, the shape of that liquid would be a cylindrical shape. What would the volume of the water be in this graduated cylinder? Well, all we would have to do is read the number on the graduated cylinder, assuming you have it on a flat surface and you are looking at it eye level to the meniscus. But you could tell exactly what the volume of the liquid water would be in the graduate. You just read it. So it would have a definite volume, but no definite shape, because if I took the water from this graduate and I poured it onto the computer, I would go all fuzzy, frizzy, and staticky right now, and I'd disappear because I'd be destroying my computer. But the water would be going all over the computer and all over the desk and all over the floor. Why? Because water, being a liquid, has no definite shape. It would take the shape of its container or the surface upon which it rests. So liquids can change shape. They're shape changers, you might say. But liquids, even though they don't have a definite shape, if you could gather up all of that water that I poured all over and not lose any through evaporation or through absorption into a sponge or paper towel or what have you, but if I could gather all of that liquid together and take its volume again, its volume would remain the same because liquids have a definite volume but no definite shape. In your notes, you might want to underline, as I have here, so that when you are studying the difference between solids and liquids, you see the distinction with liquids is that liquids have no definite shape, but they do have a definite volume. Now let's go to this diagram here as you're copying this into your notes as well. Liquids, one of the reasons they don't have a definite shape is because the particles are free to move around. They have more space. They have an opportunity to flow, or they are free to move. And the green arrows here represent their freedom to move in different directions. And again, with liquids, we call that flowing, the ability to flow. And I just want to head over to our close-up view here, and let me illustrate that for you. So we go back to our cube once again, and our cube, this is showing a solid. But if we reduce the density of this solid by removing some of the mass, in other words, removing some of the particles of matter, well, there are fewer particles now in here. And if you look carefully, these particles are now allowed to move around or to flow from one place to another. They have more space to grow, so they flow. Now, as a result, as you could probably have seen, removing some of the mass from a solid, as we go to a liquid, there is now less mass in the same volume. What could you tell me that does to the density of liquids compared to solids? Would the density be greater, less than, or equal to the density of the same solid? Remember, density equals mass divided by volume. Remember that from the first unit. And so the less mass we have in the same volume, that's going to result in a lower density. So solids generally, remember, except for water, generally have a higher density than the same material in liquid form. Liquids have a lower density because there's less mass in the same volume. Let's head back to our notes once again. So you can make a little note next to this diagram that liquids have a lower density. As we move on to our third phase of matter. Our third phase of matter is a real gas. Now, that was an expression back, I think, in the 1950s. Something extraordinary might be called a gas, or something really humorous might have been called a gas. I don't know why that was an expression back then. Maybe because if you laughed really, really hard about something, maybe some gas would come out of you. I don't know. But gases, let's get back to science here. And gases can be described as a phase of matter where there is no definite shape and no definite volume. No definite shape and no definite volume. And why is that? Well, first, think of a balloon. Let's say you're blowing up a balloon. I used to be able to do this myself, but I've blown up so many balloons in my life, I can't even touch balloons anymore. I'm allergic to latex. Isn't that awful? But you know what? Maybe I could find an alternative to a regular balloon. Hold on one moment. Here, I found something. Maybe this will work, maybe it won't. I have a non latex glove. Typically, these do not inflate very well, but I'm going to give it a try anyway. I'm going to see if I can blow this up. I'm going to fill it with gas from my mouth. There we go. I've got an inflatable, non latex surgical glove. Now, if you look at this glove right now, it's filled with a gas. Obviously, its shape is not geometric, and I can change the shape of this gas simply by squeezing. Oh, I just popped it. Oh, sorry. Let me get another one. Hold on. I have to make it even anyway. Otherwise, I'll have one glove just hanging around. So these gloves don't expand nearly as well as latex balloons or latex gloves. But all right, we'll give it another try here. Ready? I won't inflate it quite as much as the last one. All right, so we have our glove. And I can squeeze the fingers of this glove to actually change its shape. But in addition to changing its shape, you can also compress gases to change its volume. Gases thereby have no definite shape and no definite volume because by adding pressure to a gas, we can actually change its volume. Think about blowing up a bicycle tire and you have the bicycle pump up and down. You are compressing the volume and changing the shape of the air, but by doing that, you're also changing the pressure being exerted. So you can change volume, you can change the shape, but it will have other impacts. But right now, and we'll get to those later on, but right now we're focusing on shape and volume. So gases, no definite shape, no definite volume, and I bet you're wanting me to try and pop this one too, aren't you? All right, should I give it a try? All right, here we go. I'm going to pop this one. The finger keeps popping out here. Let me get them all together. All right, here we go. Oh, goodness, that went right in my ear. Oh, that was loud. All right, let's move on to the next slide. So here are gases. Gases can be described as having particles that are in constant motion. Constant motion. Again, no def. Ooh, my ear is ringing from that. Let's head over to the close-up view and let me show you what I mean. So here we left off with the gas, or rather the liquid, and we're going to remove some more particles of matter so that there are even fewer particles of matter in the same volume. Now, if we look at this, it is easy to see that these particles are able to really fly around because they have so much more room because there are fewer of them in the same volume. So they are free to float around, very, very free to fly around. Now, I have a question for you. Because there is so much less mass as a result of removing more particles, I know I didn't say that quite clearly, because there's less stuff, because there are fewer ping pong balls in here, fewer particles of matter in the same volume, what effect do you think that has on the density of gases compared to the density of solids? What do you think? Let's head back to our notes. Well, you probably got that right. Gases have the lowest density of the three main phases of matter. Because of the fewer particles and their freedom to fly around, we have less matter, less mass in a given volume, so the density is lower. Make sure you make a note of that in your notes, that gases have the lowest density compared to solids, liquids, and gases. So solids, liquids, and gases are by far the most familiar phases of matter to us. And we have probably learned about these phases of matter since kindergarten. But there's another phase of matter that is just as common, but we just don't think about it perhaps as often. So let's discuss the fourth phase of matter. The fourth phase of matter is plasma, and you see it every day. Every day you see an example of plasma. And what I mean by that is that if it's daytime, it's going to be bright out, or at least brighter than nighttime, whether the sun is shining or not. But it's brighter because of the sun is shining. And the sun is one gigantic ball of plasma, the fourth phase of matter. It is extremely high energy. We wouldn't want to put any plasma into my little transparent cube here. It would melt right through and vaporize me, and my body would go sizzle, sizzle, poof, and that would be it. I would be vaporized. The liquid in my body would be vaporized into a gas, and that wouldn't be a gas for me. But back to plasma. There's another example of plasma here on planet Earth, even if the sun isn't shining, and that is lightning. Lightning is an example of plasma as well. And as you can see with the description here, plasma is a phase of matter with very high energy. In fact, a lightning bolt itself, even though found here on Earth, a lightning bolt is about the same temperature as the surface of the sun. If you experienced a direct strike from a lightning bolt, your body would be vaporized. Your body would go sizzle, sizzle, poof, and that would be it. I've actually seen lightning strike various objects like trees. And if you've ever seen a tree struck by lightning, at the very instant that it is struck, there's like a mini explosion because all of the liquid sap and moisture that's in that tree vaporize immediately, and it's like a little explosion. And it certainly can cause the tree to catch on fire as well, which is why you don't want to be standing under a tree during a lightning storm. In fact, you want to avoid high places altogether. Stay in the safety of your own home, which is grounded electrically to preserve your life. So here we've got plasma, the fourth phase of matter. And plasma is really not something that can be contained by ordinary means. And by ordinary means, I mean like grabbing onto it. You can't grab onto plasma and hold on to it. You can grab onto a solid and hold on to it. You can grab onto a liquid and hold it in your hand. You can grab onto a gas and hold on to it as well. You don't want to hold on to plasma, folks. You don't want to scoop with your hand into the sun, and you don't want to put your hand out as a lightning rod to catch a lightning bolt because, well, let's just say bad things will happen. You cannot hold on to plasma. It cannot be contained by ordinary means. However, if you could find a way to hold on to a lightning bolt and harness the energy within, you'd become a millionaire, a billionaire instantly, because there are so many lightning bolts that strike planet Earth every day. We could power the entire world without any fail whatsoever. There's a lot of electrical energy, and you know what energy is. And I know you were humming it. But we'll talk more about that in the fourth marking period when we get to energy itself. Now, before we finish up here today, I just want to quickly review other proposed phases of matter, because it doesn't stop with plasma. Some of you may have thought, oh, yeah, there are 4 phases of matter. I know plasma is the 4th phase. Well, the more we learn about the universe, the more we realize how complex and complicated it is, and it's not so straightforward. So there have been some other proposed phases, including supersolids. Supersolids, as we kind of alluded to in the last topic of heat energy, and we talked about absolute zero, supersolids are solids that exhibit no friction to the flow of electrons through them. In other words, superconductors. Superconductors, typically at very, very low temperatures, allow the flow of electrons through these supersolids with zero friction. Again, we talked a little bit about that when we talked about absolute zero, but imagine having supersolids, no friction, zero friction. Think about what that does to the efficiency of those supercomputing machines that have supersolids. Pretty remarkable when you think about it. But it doesn't start there. When you start learning about quantum physics, perhaps in high school or beyond, you'll learn about string theory and all sorts of funky things regarding the universe. And there's another proposed phase of matter called a string liquid. I won't pretend to tell you I understand what this really is all about, but according to quantum theory, atoms are made up of smaller things, as we will learn about this unit. And some of those smaller things on their most basic level could be called strings. And it's believed that maybe some of these strings in the universe form a strange flowing form of matter called a string liquid. I've never seen it, but it's interesting to theorize about it. But string liquids, another proposed phase of matter. And of course, no discussion of matter would be complete without at least the mention of dark matter. What is it? Don't ask me. I have no idea. But dark matter is called dark matter because, well, we can't see it. But I do know that cosmologists, astronomers believe that there is so much more matter in the universe than what we can see, based on the interactions of stars, planets, and galaxies, that there must be some other form of matter that we can't see. And so we've given it the very creative name of dark matter. What it is, no one quite knows. It's just a proposed, but we are getting closer to discovering what dark matter might actually be. But who knows? Maybe one of you in your lifetime will unravel the mystery that exists in the universe and other phases of matter. But on that enticing note, I'm going to say for now, bye bye.